Graduate School at the UC Berkeley, and I think the floor is yours.
Thank you, Peter. Good afternoon, everybody. It's a pleasure to be in Barcelona. Is this on? I don't hear anything. I guess it's what it's like to be a rock star. These guys run around with a mic all the time. So now, anyway, it's a pleasure to be here this afternoon in Barcelona, as usual. The days are early and the nights are late, or the nights are early too, I hear, so we'll see how it goes. Well, in January, I had the opportunity to have a visitor come and stay with me, and this is Eduardo Artioli, who introduced me to some of the concepts of virtual element methods. And at the time of making a decision as what to talk about at Complas, that was right top of the list, and I'm kind of happy I did, because I think it's quite an interesting method, and I think it has some potential for issues that exist in computational mechanics today. So let's see if I can make this work. Okay, this is an outline of what I'll present, and I'll go through each of the topics in some limited amount of time that we have, concentrating mostly on VEM. But I thought I'd start with just a little history, because it's always nice to come back to Complas, because it's kind of graduated over the last 30 years from a small one-room conference over in the main campus with the coffee hours in the white tent just beside, as I remember. And the three people that I remember as being the organizers of this, and maybe Eugenia, you'll correct me, but I think Ernie Hinton and Roger and you were kind of foundations. And something else that happened around that time was Barcelona became the home of the first UNESCO professor, and Professor Zinkiewicz came and started, I think, probably the following January as part of that. And it was my pleasure to come and join him and his wife here for 10 years, starting in about 1995 or so through about 2005. We lived out south of here in Sitges, which is famous for other things, and we had great times there together. And I used to always wonder what they thought when Oleg and I walked around together as we went around the streets of Sitges. But I also found it was a great place to shop when your suitcase didn't arrive, because the selection of clothing was a little bit different than might have existed here around in Corte Inglés. So anyway, there's great memories that come with this, and it was always a pleasure to be a part of that over the years. It actually kind of was not too long after I retired. I retired from the university in 1994, so I've now celebrated not as many years as you have, but I'm getting close. I'm gaining on you. Okay, well, those first conferences were all about plasticity, and basically this figure was what Juan Cimne and I were working on just before Complas 1, so essentially that's part of the memories. But now you look at the list of topics that have come up and are being presented here, of which VEM is one, but the other is kind of the area of constitutive modeling, which has become much more complex over the years than what we saw in the early days of plasticity. And the things that are making it complex are things like multi-constraints that are existing in the material, which I believe that current element technology can't handle very well as we try to push our computation with current technology finite element programs. IGA may be able to handle some of this, but I think the issues are really out on some of this. So let's look a little bit about what are IGA? What are IGA? What's virtual elements that exist? Well, basically, if you start looking in 2 dimensions at polygonal elements, you start with 3 nodes and 4 nodes, nothing looks any different. But if you keep going, you get general polygonal shapes, which are quite different from finite elements, and now you begin to scratch your head as how are you going to be able to get interpolation functions for these? And I think Franco Brezzi has even pushed it further. in which you can have an element which he calls the Pegasus Element, which, if you see, is a very clever shaped element that interfaces left to right, and generally you can create a mesh out of that, and you can do analysis with it. Well, I don't think you could do that with any other kind of interpolation that I knew about beforehand, and so maybe virtual elements are a way of going forward in this. In fact, you can have admissible shapes which basically introduce the notions of hanging nodes, which then lead you to easy ways of doing adaptive meshing in terms of some of the things you do. So there's some very nice benefits that seem to come out of the virtual element technology, and we've already seen some of this from the presentation of our chairman earlier in the plenary lectures. Basically, a virtual element is defined by the order of the polynomial that we're going to use within the inside of the element, as we'll see, and we're going to call that order K, and K is basically the order of the polynomial between edges that exist on the element, and we can have K equal 1, 2, 3, etc. We've done things for 1 and 2 to some degree, which I'll show this afternoon, and we've started to code even some higher orders. I'm only going to consider 2D formulations because basically that's the easiest thing you can do in a couple of months. And we'll look at some of the things. These are the references that I use. Basically, there's a basic reference called the Hitchhiker's Guide, which exists in the Journal of Mathematical Models and Methods in Applied Science, and also the papers of my co-author, Eduardo Artioli, which is about to appear in Computational Mechanics. It's already in online. And then Peter has been generous enough to share personal communications of his recent paper on plasticity, and his first paper, I think, just appeared in August of the journal, so it's already available too. These form the basis of what I've used in terms of what I'll talk about this afternoon. So we're going to consider problems that are basically requiring only continuity of the function, basically C0 functions. We want to approximate some variable v, and I want it to be of a k-order polynomial, which means that the gradient of v is going to be a k-1 order polynomial. So let's look then first at approximating the derivative. If we approximate the derivative, we're going to talk about introducing an order of a polynomial as a coefficient, which in 2 dimensions will be a function of x and y, and then it has some parameters that define how it's related to the gradient. The issue is how to relate these parameters to the nodal parameter of the element. And these polynomials that we use, if we want an nth order polynomial, they're basically going to be from 1 up to the nth power of the polynomial. Very straightforward. So we're going to use projection operators, and then the issue is how to define what the projector will be on this variable, and its representation is given that way, and then we're just basically going to do an L2 projection of this onto the volume of the element that we want to approximate. So this is a square matrix that's made up of these k-1 polynomials, and then we have the k-1 order polynomials are going to be multiplying the derivative of the function that we wish to approximate. We apply integration by parts, which creates then 2 terms, one which is the boundary term, which is given here, and the other is a volume term that's given there. Okay, so that seems to be rather straightforward. Let's look at how we're going to approximate this. First, we can integrate these polynomials over the domain of the element, and we'll show how to do that a little bit later, and it's going to create then a coefficient matrix G alpha beta. And then we're going to approximate this integral as the line integrals with a one-dimensional interpolation using standard like one-dimensional isoperimetric interpolation on the boundary. And so the boundary integral will create a matrix, and now we have the nodal parameters of the boundary appearing in this. And we're left over then with a need to approximate the volume term. Wow, goes fast, doesn't it? Well, if k is 1, Obviously, the derivative of the k minus 1 polynomial, which is only unity, it vanishes, and so there is no volume integral. So that kind of explains why a lot of people look at k equal 1. It's trivial, there's nothing to do but boundary nodes, and you can get the projection operators directly. If k equal 2, then we have the polynomials 1x and y for the k minus 1 polynomials. And you can see if we're going to differentiate with respect to x, we'll get a single term out of the second one. And basically what's been done is you just say, well, I'll just take the integral average, and that'll call that my basis function for that average of the integral over the element. And you can continue that up to k equal 1, 2, 3. These introduce what are called moment terms within the inside of the element that have to be carried on as part of the calculation. Okay, so what we have is we have now that we can compute what those parameters were that were defining our basis functions. And it's a matter of we can express those then in terms of the nodal parameters of our approximation by just solving this linear algebraic equation. Okay, so that takes care of that, and you can see that the approximation, my derivative for the x derivative of any function, it's just a C0, which is this projector operator that I've defined, which is nothing more than my basis functions to the k minus 1 power multiplying this matrix that I just computed by the projection. And we group those together and we call those the shape functions for our elements. So now it looks like a finite element interpolation, and all we have to do is use that in the calculation of anything we want to do that involves C0 elements. So this has a nice structure that fits within something we already know how to do from how it is. And obviously we can do the same thing for the y derivative, in which we get a shape function that multiplies the parameters of the y. And without going through the details, one can go to the references and you can do the same thing, which is much more complicated to do, but it can still be done to get an approximation for the function itself in terms of something we call the shape function of the interpolation itself. Okay, that's it. So now we got shape functions, approximations for derivatives of shape functions. We're in business. Now we're finite element guys. We know what to do. We can calculate the strains for small deformation. I can calculate the deformation gradient for finite deformations, temperatures, body forces, mass. I can use displacement, mixed methods. I can do whatever I want. I can start to play my finite element game, right? Well, it's not quite that simple, as we've seen in some of the presentations. If you count the parameters and you count the functions, you find that, well, any matrix you create is not going to have proper rank, and therefore we got to do something about that. And that means we're going to have to introduce stabilizers. So you can count up functions, and you can see we're missing functions for anything other than lowest order elements like a triangle. And I don't think we're interested in a triangle, basically, at that stage, or we wouldn't be doing that. Well, we can go ahead and we can do quadratic elements. Quadratic elements allow us to, each edge now has a mid-side node. Wow. Hit two buttons at a time, sorry. Have a mid-side node that exists, so it's basically got a quadratic edge. It can be curved, so I can have curved edges. I can use different basis functions. I can use rational B-splines along the edge if I want to get conic sections out of it. So I can do a lot of things that I can mix methods that I've done. We introduced for, say, this hexagon, we would have the moment degree of freedoms would be assigned to an internal node just to fit within the structure of a finite element code, even though it has a different meaning. Okay, how do we do this? Well, we evaluate the edge values by quadrature along the edge. And we evaluate the volume integrals by dividing our polygon into triangles and then using standard barocentric coordinates to do integration over the individual triangles. You could divide this in different ways in sides, as we've seen in the earlier presentation. If we use barocentric coordinates, then we can essentially use the nice shape function properties of this. The nice thing is for k equal 1, you only need one quadrature point for the whole element. You just multiply it by the volume of the element. So it's very cheap and easy to do. What we're using is if we have straight-sided edges, we're using 3-point quadrature on the triangle to get quadratic order, and which means that I have n-edge quadratures and n-interior edges, which make it quite expensive in terms of that, because each one of these would have to pass the constitutive evaluation. If the edge is curved, I need higher order quadrature in order to pass patch tests and things like that. Okay. Well, the previous one gives a consistent term, but it's not stable. So one has to introduce a stabilizer into this, and this is probably the weak point of the method, because once you have a stabilizer, you got a parameter that has to be evaluated, and that is something that I learned I wasn't doing quite as well as I was supposed to be doing when Eduardo presented his paper earlier. So some of the things may be polished a little bit in this, but this is the classical one that's been used in the VEM method up to this point, which just uses the basis functions that we have evaluated at the nodal points to create this matrix. God, I hate this thing. God, the buttons are too close together for my stubby fingers. Which you can take the inner product of this to get this matrix, invert it, and then multiply it outer product by each of the points evaluated at the node. So it's very quick to evaluate and insert as a matrix. You need the tau parameter in terms of this. The alternative is to use the method that Professor Riggers described, in which you introduce a stored energy function in which has two terms, one of which is evaluated in a classical finite element way, and the other which is calculated from the parameters from the VEM method, and it's evaluated by special properties that have to be obtained. And I think to date, the only thing you've applied it to is the k equal 1 polynomials at this stage. I think it's conceivable to extend it, but more complicated. Okay, for that one, this is how we evaluate his parameters. We already have the centroid, so we typically divide our element into this way. We calculate the radii that appear in the scaling parameters by calculating minimal distances from the edges and the nodes, and use the parameters that are suggested in the paper by Kreisel and others to do this. Okay. As I said, we can apply this to both mixed methods or standard displacement methods. We have our shape functions. We have our implementation can be done for any stored energy function or for virtual work forms. We can use standard displacement, or we can use mixed methods, which are based upon some volumetric projection of the Jacobian. Typically, you'll find for k equal 1, everything's constant, and to within round out, there shouldn't be any difference between whether you use the mixed UP volume change or whether you use standard displacement. It depends on what you use for stabilizer. Okay, how does it look when you implement it? Well, typical element layout in our codes has a first module that calls, what kind of quadrature you're going to use. If it's a isoparametric element, we use standard isoparametric quadratures, either Gauss quadrature or Gauss-Lobato or barocentric coordinates. If it's a VEM, we have to compute those projectors and make the shape functions for our make up the projectors that will be used for the shape functions, because this will be dependent on the quadrature that we're using. We then enter the element, which is going to integrate over all the quadrature points. Going to go for interpolations. It'll look, isoparametric, IGA, VEM. Grab whatever you want for your shape function, calculate your matrix, and you're done for IGA and FEA. But for VEM, you have to add the stabilizer. So the modifications are the projectors. creation of the shape functions, and the stabilizer. Other than that, we use all the standard features of the code. We use the same constitutive models. We use the same element calculations, same linearizations. We don't use ACE-gen. We use ACE-bob. So, okay, pun my word. All right, so let's look at a couple of examples. Everybody likes to do the Cook problem. I don't like the Cook problem because it has a singularity in it, and some of the solution is going to be influential on what happens, and especially everybody likes to calculate the determinant the displacement up at this point. Well, I did the same thing. But if you look carefully at deformations with meshes, you'll see a kink usually comes out of that singular corner, which gives you a flick in the displacement and therefore biases the solution as to what the singularity is doing. So I don't think it's the greatest problem, but you got to do it because everybody else did it. So we do it. We get similar behavior. One of the things we found was the way that I'm using the stabilizer tends to converge slower than Professor Rigger's stabilizer, which tends to be quite flat in terms of this problem. This is finite elastic deformations. It's highly compressible, so there's not any problem there, plane strain. We've also done it for k equal 2. For k equal 2, the solutions are much better. The stabilizer that we use in the classical one is very good and seems to work quite well for that problem. These numbers this way are just subdivisions into quadrilaterals. The numbers in color are from the polygon mesh, which has elements that range from 4 to 7, I believe, in number of sides. And you can see the displacement value. You can plot the usual contours. You can do elastoplastic. Our model is different than the one in the Riggers paper. The model we use in this is basically one based on Papadopoulos and Liu, which is a finite deformation form of the Hill yield function, but you can set it for isotropy, so we can do that. Okay. Another problem that I like much better in terms of testing kind of how methods work for critical problems is the slot problem, which I think the first time I saw it was in a paper by Annette Mandiotti from RPI. And what it is you have this is basically a rectangular region. This is one quadrant, so you have this slot, which is a certain width with a radius of curvature here. So it has no singularities per se in the solution. It is strongly dependent on the boundary conditions that you use. Typically, there's zero normal displacements here, here, and here. And then you have the choice of whether to confine it on the outside or to let it go. In other words, you can have a traction-free or you can have one in which you have boundary constraints. Okay, we use this first to show that we can calculate mass matrices and we can calculate frequencies. And you can see that the behavior is reasonably consistent for the first 5 frequencies using both FEA, just Q1 and Q2 elements. These are bilinear, biquadratics, and the VEM, k equal 1, k equal 2. You can get reasonably good first frequencies of this. This is some of the details of what mesh looks around the boundary. Our elements do have curved sides at this, which are polynomial approximations of the circle. Okay. This happens to be what the mode shapes look like for the first 5 modes. They're consistent between the finite element and that. So it proves that we can calculate mass matrices and we can calculate reasonable low frequencies for the calculations. Okay. The other thing we did was to do this one for finite plasticity, again with the same model, with properties that are given, which are, I think, same properties roughly that Professor Riggers used, scaled to the values that are required for the Papadopoulos model. And we do this for 2 types of boundary conditions. We do it for the free right side, and you can see, you get a standard curve in which you get quite flat plateau, which is basically just the hardening modulus. But if you fix that right boundary on it, then you really make this thing work in the hardening regime. And it's a very severe test problem on robustness of elements as to whether it's going to work in the finite deformation plastic. And what we found out was we're getting some divergence, and these divergences are all due to the stabilizer. So essentially, the key to the success of this is going to be how good the stabilizer is. And that's the thing that I think requires probably a lot more study as time goes on with this. Other than that, the results seem to be pretty good. For the one with free right boundaries, the plastic zones, which are given here in terms of the contours of red, are pretty consistent between just standard Q1P0 finite elements, which aren't absolutely stable, and the K equal 1 polynomials. K equal 2 looks pretty much the same. But if you fix the right boundary, you get some differences which are a little bit disturbing. For example, you'll see that there's a contour here, which doesn't exist in the finite element. Okay, we did not do mesh refinement on this, so I don't know what it looks like under refinement. Let me finish up then with just one last thing to show that one can easily do adaptive mesh refinement with these kind of schemes, because you can introduce hanging nodes on the edge of the elements. So this is K equal 1 approximations, and you can see that we've introduced some hanging nodes at the middle here, and one then can do refinement of the mesh in the contact zone. And this is one level of refinement. There's one with second order in terms of it. So it has some very desirable features in terms of that, in terms of the fact you can just introduce hanging nodes to do the refinement in rather a straightforward, easy way. Okay, so this is what I've tried to present in this in terms of the kind of things we've looked at in 2D VEM. The key to our implementation is to introduce the idea that we get shape functions out of this, and therefore you can slam it into a finite element code in a very straightforward, simple way without having to rewrite a lot of things. The critical factors are the stabilizer, obviously. The choices seem to be very robust for small strain. Good for finite deformation elasticity. The plasticity is much more delicate and seems to be something that we need to look at more. Our next efforts are to be able to solve dynamics problems, and also to look at applications to some of the more modern constitutive models which have higher constraints than just volume constraints, such as stiff fibers in multiple directions, which I think is really something that, if you look critically at current finite elements, is prone to a difficulty. Okay, the other thing that's happened at this is Roger's 75th birthday. I guess I don't think he's here, but... Oh, you're here? Oh, my eyes aren't that good, Roger. Anyway, but Roger has been a friend for a number of years, and we shared some delightful times together in South Africa in the 1990s. I don't remember which one, Roger, but it was one of them, and my wife was here. We really had a great time, and Roger was very instructive. And also, I was pleased to see and be with Roger in 2013 when he was inducted into the U.S. National Academy of Engineering. So happy birthday, Roger, and happy many more to come. I hope to be here to celebrate your 80th and the 85th, etc. We'll see. The other thing that's kind of been a sad year is that a lot of our friends of the last 30 years have gone on to greener pastures, and the last year has been one of losses of two friends, not only Christian Mia, but Oleg's wife, Helen, who died late December. So I certainly would like to remember them and also acknowledge the joy that they brought to conferences of this kind and to my life over the last several years. So with that, I'd like to stop and thank you all for your kind attention.